Hello, and welcome to the Module 8.5 Simplifying Radical Expressions Notes. Our objective for today is that I can simplify square roots and I can simplify cube roots. Now, this is going to be a lesson where we are going to build on what we did yesterday. Yesterday we were dealing with moving things into and out of radical form, and we were worried about doing some simplifying, and we had a lot of work with perfect squares. Now, today, what we're going to do is we're going to look at things when everything doesn't work out to be a perfect square, or a perfect cube, or a perfect nth level radical, whatever that may be. So, a couple things. A radical expression is an expression that contains a radical, such as a square root. Could be a cube root, could be a fourth root, whatever it may be. A perfect square is a rational number with a square root that is a rational number. And the principal square root is going to be the positive solution of a square root. Because if we remember, the square root of 4 gives us plus or minus 2 as our answer. So the principal one is going to be the positive one. And so that would be a positive 2 is our principal. So that would be the principal root. Now we have two properties that we're going to be working with: the multiplication property and the division property. So the multiplication property says for any numbers a greater than or equal to 0, b greater than or equal to 0, the square root of a and b, ab, is equal to the square root of a times the square root of b. All right, so we have two things that we're both taking the square root of. We can either combine them into one square root if we have two roots, two radicals being multiplied together. We can combine them under one radical symbol, or we can split them apart. And if it's already under one, we can split it into two. So for example, square root of 48 is the square root of 16 times the square root of 3, because 16 times 3 is 48. And then we can simplify from there. The square root of 16 is 4, and the square root of 3 is 3. Or square root of 3 is something we can't take the square root of. All right. The division property of square roots is going to work exactly the same way. If we have division, a fraction that is underneath our radical symbol, we can separate it into two separate fractions and treat each one, two separate radicals, and we can treat each one of them individually when it comes to simplifying. So the square root of 36 over 49. Well, square root of 36 is 6, the square root of 49 is 7, so that square root reduces to just 6 over 7. So when is a square root in its simplest form? It's when these three conditions are going to be true. The square root contains no perfect square factors. So all perfect squares have been removed from your radical, except for one, obviously. The square root contains no fractions. And there are no square roots in the denominator of the fraction. We do not want square roots in the denominator. That's a problem. We're not going to do it. So let's simplify a square root. So first off, we have the square root of 72. Now, if we know our perfect squares, this is certainly going to be helpful. So I recommend having memorized the perfect squares between 1 and 15, because those are the numbers that are going to come up most common in algebra. Okay, so I know that I've got perfect squares. Well, 8's perfect square is 64, and then 9's perfect square is 81. Neither one of those are 72. So I don't have a perfect square on the surface. But let's break this down the way we did yesterday, and let's look for our factor trees. So 72, it's an even number, so I know that I can divide by 2, because I don't know the factors of 72 off the top of my head. And so we have 36. 2 times 36 is 72. Now, I do know that 36 is a perfect square, which we break down and we get 6 times 6. Since we're doing a square root, we're looking for groups of 2 of something. And I have a group of 2 of something. So I can take the square root of 36 and it's going to be a 6. That's it. So that tree is done. I got to my square root. On the other part of it, I have a 2. There's nothing to go with that 2, so it needs to stay underneath the radical symbol. So you have 6 square root of 2. All right, letter B. We have 8. 8 is made up of 2 times 4. And 4 is made up of 2 times 2. Again, we're looking for groups of 2 of something. We've got 2 2's here. So we bring it to the outside. We'll bring a 2 out. And then what's left on the inside of the radical? A 2. Right? So that's the other piece that was still left inside it, right? It's 2 times 2 times 2. And so that's another way of thinking of this. If we separate this out into its factors, you could say this is the square root of 2 times 4 under one radical, which separates into the square root of 2 times the square root of 4, and that would be square root of 2 times 2 on the outside. So you can get to it multiple ways here, but that's the thinking that we're seeing here. When we split this into our factors, we're looking for what are my perfect squares. Now, do you always need to show all of the factor trees all the way down to your prime factors? No. If in letter A, we stopped when we got the pair of 6's. As you get better at this, you're going to stop when you get to that or that, because the square root of 36 is 6, the square root of 4 is 2, right? So you're going to get to those perfect square factors, and you're going to be able to stop and do, figure it out right away from there. But that's going to take time of you working with these problems and working with the factors and learning them better in your own head. All right, so 125 ends in a 5, so I know it's divisible by a 5. And 125 divided by 5 is 25. If you remember from our work yesterday, that is simply 5 cubed. Again, we're taking the square root, so we have one pair of 5's, so we bring that out, and we have left inside our radical a 5. All right, you guys try letters D, E, and F on your own, and then check your work against mine. All right, the square root of 48. We can work this a number of ways. I'm going to separate it out as 48 is 4 times 12. And I'm intentionally doing it this way because it may not have been the way you did it on your own. 12 breaks up into 4 and 3. Do I have a pair of factors that I can take out? I do. I have a pair of 4's. So we bring out a 4. What's left inside my radical is a 3. Now, could I have done this differently? Could I have taken those 4's to their prime factors? I could have. Right? Then we've got factors of 2 and 2 that get brought out. So we would have 2 factors. So we have a 2, and we're left with the square root with 3 remaining in it. 2 times 2 is 4, root 3. So if you were to take a problem, you can never over factor and oversimplify one of these questions, right? You can take it all the way to the prime factors if you want to. Get it all the way down to a prime number, something that's not divisible by anything other than 1 in itself. You'll be able to get your correct answer. You will simplify correctly. It just might mean that you did a little bit further down, a little deeper of a factor tree than you necessarily needed to, right? But if I didn't see it on the surface, if I didn't remember that 4 times 12 is 48, and I started with dividing it by 2, and I had 2 times 24, then I can still work my factor tree down, and I can still get those pairs of factors that are going to come out. You will still get the same perfect square terms, and you will still be able to simplify it to the same point. It doesn't matter which is the first factor that you choose to divide by. All right, letter E. So 32 is even. So I know I can divide by 2, right? And I'm going to just give you a hint. When things are even and you're not sure immediately what you could divide by, just go by 2 right away, right? It's going to maybe take you a little longer to work your way down the tree, but it's going to help you out because you're going to be able to get to some numbers that you know eventually. So we've got a 2 and 16. 2 times 16 is 32. 16 breaks down into 4 and 4. That's a pair, so we bring that to the outside. What's left in our radical, what doesn't have a pair? That 2 does not have a pair. So 4 square root of 2 is the simplification. All right, letter F. This is a prime example of I don't know factors of 324 other than it's even, so I divide by 2. And when I use a calculator to do that, I get 162. Again, not something that I'm super familiar with that I work with on a routine basis, but it's even, so I divide by 2. Okay, divide by 2. And when I divide 162 by 2, I get 81, which now that is a familiar face. And so I bring out my terms. I have a pair of 9s. We have a 9. I have a pair of 2s. I have a 2. They're being multiplied, remember? Do I have anything left inside of my radical? No. All of my terms have been taken care of. So really, this is 81 times 4 is the two terms here. So 9 times 2, that is 18. And we are simplified. All right, to the next page. We are going to multiply square roots now. So in this, we're going to use that multiplication property of square roots, and you'll remember what it says is that you can combine these under one radical sign. Now, your textbook is going to show you to multiply these two numbers right away. I don't like to do that. The reason I don't like to do that is it puts me in a position where then I'm having to do a factor tree and figure out factors of a larger number when on the surface right here, I have taken the first, just by combining them, by not multiplying them, I've done that first level of the factor tree, right? I could do 5 times 48, and it's going to get me what? 5 times 48 is going to get me 240. Well, I already did my first step of a factor tree by figuring out that 5 times 48 is 240. Like I've got that first level, right? So now I'm going to break it apart. So 48 is going to break into, we just did this, 4 and 12, and 12 breaks into 4 and 3. So what are my pairs that I have? I have a pair of 4s that I can bring outside the radical. I don't have any other pairs, but what is still left? I still have a 5 and I still have a 3. Those two values remain under the radical symbol, that one and that one. They're still in those trees. They're still inside the radical, right? You can picture this as there's a box here, right? And those numbers are still trapped inside of it. They don't have the pair that can get them out. So the 3 and the 5 stay inside that box. All right, now we just need to simplify and do our multiplication. So when we do that, we have 4 times the square root of 15. Okay. Letter B, we've got the square root of 8 and the square root of 14. So let's combine that under one radical. We have 8 times 14. Well, what are my factors? The factor of 8 is 2 and 4. The factors of 4 are 2 and 2. The factors of 14 are 2 and 7. So, what are my pairs? What pairs do I have here? Well, I have a pair of 2s. I have a pair of 2s. And I have a 7. So, I bring those out. We have one pair of 2s. We have a second pair of 2s. We've got our radical, and what's left inside the radical is our prime factors, is a 7. And now we do the multiplication on the outside. 2 times 2 is 4, square root of 7. All right. Letter C. Combine it under one radical first. 10 times 30. Now, I can take this to a prime factor if I wanted to, but I'm going to just make a little logical leap. I know that 30 is 10 times 3. And there I go. I get my prime factor. Well, I get my factor. It's not the prime factor, but I get the factor. And it's 10, and we've got the square root of 3. Now, if we had multiplied these, square root of 300, you could easily see 300 is 100 times 3, and the square root of 100 is 10 times the square root of 3. All right, there are 3 you-try problems that I would like you to do on your own, and then check your work against mine. All right, letter D. We combine this first under one radical. We have 7 times 42. 42 is going to break down into 7 and 6. I don't need to go any further because there's my pair of factors. So we have a 7 that can come out, and what's left is the square root of 6. Letter E. Combine it under one radical first. Okay, so we got 6 times the square root of 24. When I break 24 into factors, one of my ways of breaking it up would be 6 times 4, and that gives me a pair of 6s and a pair of 2s that can come out. So we have a 6 and 2, and 6 times 2 is 12. Okay. And if we look at letter F, we start off, write it under one radical. We have the square root of 12 times 27. That's an odd one, but okay. So 12 is 4 times 3. 4 is 2 times 2. 27 is 3 times 9. 9 is 3 times 3. So again, let's look for what are my pairs? I've got a pair of 2s. I've got a pair of 3s, and I've got a pair of 3s. So I'm going to bring each one of those out. So we have a 2, a 3, and a 3. And when you multiply those together, 2 times 3 is 6, times 3 is 18. Okay. So example 3 is going to be dividing square roots. So we are going to work with division of square roots. All right. Now, when I look at this, the first thing I always want to do is I want to simplify a fraction if I can first. 24 over 27. Can I simplify that fraction? Can I reduce that fraction? Well, they are both divisible by 3. So I can rewrite this fraction as the square root of 8 over the square root of 9. Now, when I break apart my factors, and we're going to do this kind of 2 steps at once. So we're going to split it into the square root in the numerator and a square root in the denominator. And I'm going to break it into its prime factors. Now, 8 is something that we're easily workable. It's 2 times 2 times 2. And then the square root of 9 is 3 times 3. So when I get to looking at my pairs, I've got a pair of 3s and I've got a pair of 2s that are going to come out of my radicals. So I'm going to have a 2, and then I'm left in the numerator with the square root of 2. And in my denominator, I have a 3. Now, if we look back to the first page, or think back to the first page, a square root is simplified if it contains no root other than no perfect square root. We don't have any perfect square factors. That the root contains no fractions, so there is no fraction inside the square root, and there are no square roots in the denominator. That is canceled out, so we are good to go here. All right, letter B. We've got 28 over 16, and we're taking the square root of that. 28 I can simplify over 16. Well, those are both divisible by 4. So my first step is going to be divide by 4, and I get 7 over 4. And now I'm going to break it down into two different radicals, and I'm going to break out the factors. So the square root of 7, nothing I can do there. 7 is a prime number. Square root of 4 is 2 times 2, which gives me a pair of factors that I can bring out. And so I'm going to have the square root of 7 over 2. And that's the simplified form, square root of 7 over 2. Letter C, we have 14 over 63. Well, let's look at this another way. If I didn't simplify, how would this look? So we would start by splitting it into its two components. So 14 is 2 times 7 over square root of 63 is the square root of 7 times 3 times 3. Now, we have a square root. We've got a pair down there, so we're going to bring out a 3 in my denominator, and I'm left with the square root of 7. And the numerator, we've got square root of 2 and square root of 7, right? Because either one of these, neither one of those can be simplified. Now I have two square roots of 7, right? That violates, I've got a square root in the denominator. That violates my rule. However, square root of 7 divided by square root of 7 is going to cancel out, and I end up with the square root of 2 over 3. Now, had we simplified this, divide numerator and denominator by 7 before we do anything else, you would have the square root of 2/9. Square root of 2 stays square root of 2, and then you've got the square root of 9, and that is 3. So you have the square root of 2 over 3. All right, I want you to try letters D, E, and F at the bottom of this page on your own, and then check your work against mine. All right, so we've got the square root of 64 and 16. I know that that is two perfect squares, so we've got the square root of 8 times 8, square root of 4 times 4. There are pairs in both of those. The square root of 64 is 8. The square root of 16 is 4, and that can be simplified. You must simplify all fractions in this class, and so the result of that is 2. Now, if you had simplified beforehand, you certainly could do so. And then you would just have the square root of 4, and it would have been 2. Letter E, we've got the square root of 14 over 18. So that can be divided by 2. So I've got the square root of 7 over the square root of 9. I know that the square root of 7 is simplified. Square root of 9 is 3. And letter F, we've got the square root of 50 over the square root of 4. Well, the square root of 50 is the square root of 25 times the square root of 2, or it could have been written under one radical. And then we've got the square root of square root of 4, since we're not breaking everything apart. Perfect square, square root of 25 is 5. Square root of 2 remains the same. Square root of 4 is 2. And that's your final answer. All right, we're going to go ahead and go to the next page now. On the next page, we are now going to be simplifying square roots with variables. All right, so couple different strategies to walk through how to do these ones with variables, especially ones that have variables with higher roots or higher powers than just a 2. So one way is, well, if I know the x to the 4th, I can split that into two terms. One of them is x squared and one of them is x squared, right? So if it's an even number, I can divide it in 2 and have the x to that divided by 2 power, because they just add together, right? We're splitting it in half. And that gives me a group of 2 that I can take the square root of, and the square root of x to the 4th is x squared, right? We're looking for what times itself is going to give us x to the 4th, and x squared is that. Now, again, there is an alternate way you could do this, and you do it with, you divide by, or to x squared, and you go by x and x, and x and x, and then again, you have one group of 2 groups, so x times x, which is x squared. You could approach this another way. And the other way you could approach it is, instead of going into groups of 2, you could just break it out into x to the 4th is x times x times x times x. And again, you're getting a group of 2 x's and a group of 2 x's. So it'll be x times x, which is x squared. So that's multiple different avenues you can take with these variables. All right, letter B. So this is one where we get a little more complex, and it's just going to get a little messier because you've got a lot of stuff going on. Now, this first one, x to the 3rd, we've got 2, so we've got an odd number. So what you could do is say, well, x to the 3rd is just x squared times x. Let's make that 2 look a little better. So x to the square, x to the 2nd power times x, right? We just separated out that odd number. And then x squared is x times x, and I'll switch up the color here. Y to the 6th, again, if we it's an even, so if we divide it by 2, we get y to the 3rd, y to the 3rd. And then z, we've got z, and then we've got z to the 4th, which then we can divide in half and be z squared, z squared. So now, when I highlight, what are my pairs? I have a pair of x's right there. I have a pair of y cubeds, and I have a pair of z squareds. So each one of those elements gets brought out. So we're going to be left with, we have an x, we have a y cubed, we have a z squared. Is anything left under my radical? I have that lone x and the lone z. So it's x, z. So the simplification on that is x y cubed z squared to the square times the square root of xz. All right, letter C. Letter C, we've got the square root of 32 x to the 7th y to the 8th. Okay, so now we have an expression that's not just variables or numbers, it's variables and numbers. We follow the exact same process. 32 divided by 2 is 16. 16 breaks into 4 and 4. There's my first perfect square factor. X to the 7th, we're going to do an x, and we're going to do an x to the 6th. X to the 6th breaks into x to the 3rd, x to the 3rd. And we've got y to the 8th, which will be y to the 4th, y to the 4th. So x to the 3rds, that's a pair. Y to the 4th, that's a pair. So what am I left with? Well, let's see. We bring out a 4. We have an x to the 3rd. We have a y to the 4th. And what's left on the inside? We have a 2 and we have an x. So square root of 2x. Letter D, we're factoring in division this time. So 24, I know a perfect square that's in that, and it's going to be the 4 times 6, and x to the 5th, well, that's x to the 4th times x, over square root of 36, well, I know that's 6 times 6, and we're times y cubed, y cubed. So when I look for my factors to bring out, right, square root of 4 is going to give me 2. Square root of x to the 4th gives me x squared. and I'm left with a 6 and an x. Now, I didn't bring 6 to prime, but I know that 2 times 3 is, they're both prime factors, right? In the denominator, the square root, we have a pair of 6's, so that comes out. And we have a pair of y cubed, and so that comes out. And so you get 2x squared times the square root of 6x over 6y cubed. And can I simplify that? I can. 2 over 6 reduces to 1 over 3. So it ends up being x squared times the square root of 6x over 3y cubed. All right. And next up, there are 4 U-try problems. You go ahead and try them on your own and then check your work against mine. All right, letter E, x. Can't do anything with that. Y is y to the 6th times y. Y to the 6th is y to the 3rd. Z to the 4th breaks into z squared, z squared. So, y to the 3rd is a pair. X squared is a pair. So we go ahead and bring those out. We have y to the 3rd. I apologize, I misspoke. I said x squared. It's z squared. And then what's left in my radical? We have an x and a y. So you have y cubed, z squared, the square root of xy. Okay. Letter F. X to the 3rd, we break that into x squared. And x squared is x times x. Y to the 6th is y to the 3rd, y to the 3rd, z to the 5th. So we've got a, and this didn't get changed. This was supposed to be a different problem. So we're going to fix that now. So what's printed out on your sheet is going to look like this instead. All right, so you're going to have the square root of 20 x to the 3rd, y to the 7th, z. All right, so now when we go ahead and we simplify those, 20 simplifies to 4 and 5. X squared turns into x, or x cubed turns into x squared and x, which breaks down into x times x. Y to the 7th, I'm going to change pen colors because this is getting a little tight here. Y to the 7th is going to be y to the 6th and y. Y to the 6th is y to the 3rd, y to the 3rd. And you have z there, which has no exponent. So let's start breaking down what are our pairs. Well, square root of 4 is going to give me 2. We got a pair of x's, pair of y cubeds, and that's what I got. So we go ahead and simplify that. Square root of 4 is 2 x y cubed, and we're taking the square root of what's still left. We have a 5, we have a y, we have a z. So 5y z. Okay, and we have an x. So it's 5x y z. And on the outside, it's 2x cubed. All right, so the next one, let me go ahead and correct this. So our next one is the square root of 27 x to the 18th, y to the 9th. All right, so let's break that down. 27 breaks into 3 and 9. 9 is 3 and 3. x to the 18th is x to the 9th, x to the 9th. Y to the 9th is y, and y to the 8th. Y to the 8th is y to the 4th, y to the 4th. So let's find our pairs. We have a pair of 3s. I have a pair of x to the 9ths. I have a pair of y to the 4ths. And I'm going to bring those out now. So I have 3 on the outside. I have an x to the 9th. I have a y to the 4th. And I have the square root of 3 and y remaining. So that's 3x to the 9th, y to the 4th, times the square root of 3y. All right, letter H. Letter H. We're going to simplify. We have to break apart those fractions. So we have 24 is 4 times 6, and then we've got an x. And then in the denominator, we have the square root of 16 is 4 times 4. We've got x to the 4th x. So square root of 4 is 2. And then we've got square root of 6 and x. In our denominator, square root of 4 times 4, well, that's a pair. So that's the square, that's 4. And then we've got x to the 4th, so that'll be x squared. We have square root of x. Well, if we remember, I can rewrite that top portion, and instead of being square root of 6x, it's square root of 6 square root of x, and now I simplify, and I get 2 square root of 6 over 4x squared. All right. So let's take a look at letter A here. Sarah uses an online calculator to determine how much interest she would accrue in a savings account after 2 years. She plans to invest $750, and the calculator determines that she could have $780 after 2 years. She can find the interest rate R of the savings account by using the formula R equals the square root of A over P, all minus 1, where A is the amount after 2 years, P is the initial investment. What is our interest rate? So A is the amount after 2 years. So that would be $780 after 2 years. P is the initial investment. Her investment is $750. We want to know, what is the interest rate? R. So R is our unknown. So let's figure this out. We are going to just start by substituting into our equation. So we have R is equal to the square root of A, 780, over P, 750, and we're subtracting 1. Now, when I simplify this, I can find some division to do. And it looks like I'm dividing by 30 maybe? Yeah, I would divide by 30. And so when I do that, my fraction on the inside is the square root of 26 over the square root of 25, and this is minus 1. And then when I simplify that, we get the square root of 26, because that's 2 times 13, over square root of 25 is 5 minus 1. Now you're going to need to use a calculator to actually do this work now. And what you're going to get is the approximate interest rate is 0.0198. And we remember interest is a percent. So when it's a decimal, we write it as a percent. So that's approximately 2%. So she got 2% interest approximately on her $750. Not a great return on investment, although in a lot of years it keeps you in the neighborhood of inflation. You're not making any money on that, but you're not really necessarily losing any money either. All right, so letter B. We've got the optimal order quantity Q is the number of items a company should order to minimize costs. If an item costs $5 per order and each unit costs 40 cents to store for 1 year, then the company can find Q by using Q equals the square root of 25D over 2, where D is the annual demand, or how many people would buy the product if it were available. If 1,125 people would want to buy their product in a year, how many items should the company order? Okay, round your answer to the nearest unit. So let's go ahead and let's do this. This is going to be a straight calculator problem. So when we set this up, we say Q is going to be equal to the square root of 25 times our D, which was the demand in a year if it were available. And so that would be the 1125 is our demand. So 25 times 1125 over 2. All right, now you're going to actually do that. 25 times 1125, and you get Q is equal to the square root of 28 125 over 2. Okay, and when I do that, type it into your calculator because these are numbers that are rather large. And you're going to get that Q is going to equal 118.59, which means it's approximately 119 units. So if this company was ordering the ideal amount of a product, they would order 119 units. And that would match this measure Q. All right, we are going to flip to our last page. And in this, we are going to find higher roots. So we're going to find fourth roots, we're going to find third roots. The process is still going to be exactly the same. We're just going to be looking for different groups of numbers. We're looking for more in the group, right? So if it's a fourth root, in order for us to take the fourth root, you need to have 4 of that value to take out. So 405x to the 5th. So 405, that ends in a 5, so I know it's 5 times something. It's 5 times 81. 81 is 9 times 9. 9 is 3 times 3. X to the 5th is x to the 4th times x. So if I'm looking for groups of 4, I have a group of 4 3s there, and I have a group of 4 x's there. So I am going to bring 1 of each to the outside. So we have 3x times the fourth root of, we have a 5 remaining, and we have an x remaining. 5 and x. All right, letter B. We have the third root, or the cube root, of all of this stuff. So 15, let's break that down. We're going to do a new square root. So 15 is 3 times 5. X squared is x times x. Y cubed is y times y times y. Z to the 4th is z, 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 z. Hopefully you're not catching some z's while you're doing these notes. Now, our denominator, 81 is 9 times 9. 9 times 9 is 3 times 3 times 3 times 3. And we've got x to the 5th. So x, 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 x. All right, we could do this one of two ways. One way is just find how many groups of 3 we have and bring them out. I have a group of 3 y's. I have a group of 3 z's. In the denominator, I have a group of 3 3's and I have a group of 3 x's. So let's bring those out. So I'm going to have a y and a z times the square root of, we have, well, let's do these as individual roots. We have the square root of 3, square root of 5, square root of x, square root of x, square root of z. All of this is over. We bring out a 3. We bring out an x, and we've got the square root of 3, square root of x, square root of x. So now I look and see, do I have things that I can simplify? Well, square root of 3 over square root of 3, that cancels out. Square root x, square root x, square root x, square root x. And what am I going to be left with? We have yz square root of 5z over 3x. Now, if we go back a step, can I look to the inside of this and simplify inside of my fraction? Absolutely, you could. You could say 3 and 3 cancel out. X and x and x cancel out. You could have simplified that before you did the square roots. So I suggest simplify inside the fraction if you can. It's less work on the back end. You guys try letters C and D on your own and then check your work against mine. Letter C, 256. That breaks down into, let's see, we have 4 and we have 64. 64 is 8 times 8. 8 times 8 is 4 times 2. Okay, and I think I'm good there, but hey, you know what, why don't, let's go everything, let's go to prime. So I have all my prime factors. Now, x to the 6th and x to the 1st is going to be the simplification there, and y to the 3rd is going to be y times y times y. X to the 6th, well, we need groups of 3, so if it was square root, we divided it by 2. Cube root, we're going to divide by 3, and so it's going to be x squared, x squared, x squared. If you wanted to, you could then x, 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 x. So that's everything taken to prime. So we're doing the cube root, so we're looking for groups of 3 of something. So we have 1, 2, 3. 1, 2, 3. 1, 2. Okay, so we got 2, we've got 1, 2. All right, so now we need to look at our x's. We've got a group of 3. We've got a group of 3. And our y's, we've got a group of 3. So now what do I have left on my, or what am I bringing out? So I had one group of 2's. I had another group of 2's. I had a group of x's. I had a group of x's. I had a group of y's. And what was left inside my radical is a 2, and an x. So we simplify. 2 times 2 is 4. X times x is x squared. Y to the 3rd root of 2 times 2 is 4, x. All right, letter D. You are taking the cube root again. So 216, I don't know factors of that. I know that's going to be a 2 though, because it's even. And when I do that, it's 108. 108 breaks into 2 and 54. 54 breaks into 6 times 9. 6 breaks into 2 times 3. 9 breaks into 3 times 3. And then we've got x to the 5th was x times x times x times x times x. Y squared is y times y, and z is just z. So if I look for my groups, we're looking for groups of 3 of something. So I have 3 2s. I have 3 3s. I have 3 x's. That's all that I have grouped. So I bring out a 2. I bring out a 3. There's no coefficients left. I bring out an x. What do I have left on the inside? My coefficients are gone. I have 2 x's, so x times x. I have 2 y's, y, y, and I have a z. And now I rewrite it. 2 times 3 is 6. X times the square root of x squared, y squared, z. And that's the end of our notes for tonight. If you have any questions, bring them to class tomorrow. Otherwise, I hope you have a great day.